it's not a surprise for me. It's happened before. It will probably happen in the future too. So this course is several different students with different student specializations have this as a mandatory course, and conflicts happens. And that's definitely happened this year too, but I think it's better. No, at least they have put it in front, not going later in the semester. So
you can get rid of the exams as soon as possible.
Yeah, so that's was what they hoped, that the normally students are pleased with getting the exams done early as possible. So, yeah. So, but that's the what's important to know, and it will be a digital exam. So
even for us.
For all of the students.
Even for us?
For all students. There are no exam rooms that will be available at the university. So the people who are organizing the exams typically are in the risiko. They are elder people, and they shouldn't be exposed to potential corona. So that's the way it is. And so everyone, digital exam, you do it at home, you have all available material, and definitely there may be a small changes in how the exams is put up compared to last year's difference. So you can't make new problems in PVT. But definitely there will be some focus on that. So we are in week 40, and the plan, as planned, we are going to look into vapor liquid equilibriums today.
Excuse me, both, we have one exam or both, two exams? One exam for geology, one exam for PVT?
It will be one exam for all. So it's a 4 hours exam. So 2 hours is reserved for, not reserved, but you can, if you want to spend 4 hours on PVT and no hours on Geo is okay. Maybe not that okay if you do it the opposite for me, but you never know. So the 4 hours, the 2 parts in the exam, but totally 4 hours.
And 50%?
And they count 50-50, yes. So that's the 50% on each during the evaluation. That's correct. So and it's a digital. So you scan, you write on paper the answers, and you use your mobile phone and take picture of the pages and deliver it. And I think there will probably be an update on how it's done. It was done last semester and it went quite okay. And I think you will be allowed to have 30 minutes to complete the delivery. So 4.5 hours totally. But you should test out that you are aware of how to do it. So you are familiar to the scanning system with the mobile phone and get things delivered in time. Because it's a little bit dependent on yourself too. But there is always possibility to do the exam next year. Always hopes. Okay, so that was today.
So Professor, is it like next year or is like each semester?
If
you need to retake the exam, so
no, if you fail the exam, it is next year. But if there is a good reason for it that you couldn't have the exam this year, then you have an opportunity next semester, early next semester. So that's the way it is. Okay, so problems, and I think the student assistant has published some videos today for solutions. At least he was going to update it when I talked to him 1 hour ago. So there are some So he has made some videos on problem solving. So we should now be more or less finished with the first 1, 3, and 4 linked to gases. And now when we're going through the last part of vapor liquid equilibrium, so you should also be able to do all the exercises that are linked to oil with dissolved gas. So that was the plan, and the plan for the next week is that that's not correct. Next week is we will have laboratory exercises. So no lecture next week on Thursday. So the student assistant will do some exercising, solving. We can concentrate on that. And week 42, we will do the gas condensate and also look into equation of state, a short touch of it, so you are aware of what's happening in a PET simulator. So so the plan is 2 more hours after this, 2 more hours on lecturing, and then the rest of the time we spend on problem solving. And it will be included 2 exam sets. That's the plan for that the PhD student, no, that the student assistants are going to work. Yep. So today, vapor liquid equilibriums, it's a little bit PVT. Definitely there is vapor liquid, and in most cases we are working with vapor liquid equilibrium. So it could be in the reservoir, it could be through the production system. So we need a better understanding of it. But generally today, most of these problems is solved with the use of a PVT simulator. It's nothing that we spend a lot of time on doing calculation on paper. But you should be aware of what we are doing and how we can simplify calculations when we are doing calculations on paper. So that's the plan. So if you look into the vapor liquid equilibriums, we have a large variety of components in the crude oil, from small molecules to asphaltenic molecules, and the interaction in between these molecules is not very in models and things like that. So at relevant and that's one of the problems at relevant P&D. We should expect at least 2 phases present. There could be a solid phase too, because of the asphaltene and resins may precipitate. And there's also a water phase that also could be a part of the system. So we should be aware of. And as I said, equilibriums between gas and liquids are formed. It could be in the reservoir, and we have pressure drawdown. It could be at separator conditions or through the production system, and definitely also at standard conditions. So we have, so it's a little bit important to understand. And most of these calculations, as I said, vapor liquid equilibriums are based on equilibrium constants when we calculate it. That's what we are using when we are using a PVT simulator. I'll come a little bit back on the definition of equilibrium constants for the individual components in the fluid. So this is a figure trying to describe what's happening in a 2-phase system. We have a gas and we have a liquid. And when we have equilibriums, there is a condensing and a vaporization taking place. So over time, the systems are in a way established some sort of dynamic equilibrium. Definitely, if the oil column is large, there may be also segregation within the oil column. So the diffusion is not enough to maintain the same composition throughout the whole column. So then we may also have segregation. So if I take oil in the bottom of the column, it may not have the same composition and properties as the oil close to the gas oil contact. So, and the gas phase will establish some sort of equilibrium in the composition for the gas, and we have a composition of the individual components in the liquid phase. And the equilibrium constant then is defined as the composition of the individual components of gas divided by the composition of liquid for the individual components. And as I said, complex system to calculate, difficult to do it in most cases on paper. So today we are dependent on the composition analysis, and when we have a composition analysis of the fluid, then it can be handled in PVT simulators. So if you look into the fundamental understanding of the definition of K equilibrium constants, it's in a way based on Dalton's law, ideal gases. Then we know that the pressure is the sum of the individual components. So then we can, in a way, the pressure of the individual components could be expressed by the composition of the individual components, the molar composition of it, multiplied by the total pressure of the system. So that's a way to represent the pressure of the individual components. And then we have a theoretical approach on using the Rolf's law. And then we say that the pressure of the individual components is the molar composition of the individual components multiplied by, or the mole fraction of the individual components multiplied by the vapor pressure of the individual component for an ideal system. And so the vapor pressure is when we go to the vapor, you have a temperature, go up to the vapor, liquid interface, and we have a vapor pressure for the system.
This is for pure component.
Yeah, this is for a pure component. So then I can find the vapor pressure for the individual component. So they are table values. And then I can combine Rolf's and Dalton's law, and I come up with this theoretical approach for an equilibrium constant. And Ki is the equilibrium constant at the particular temperature and total pressure. So two factors that restrict the use of equilibrium constant calculated by Rolf's and Dalton's law are immediately apparent, and a pure component cannot have a vapor pressure at temperature above its critical point. So when you're working with methane and ethane, they have very low critical point for the gases. So it's not valid for reservoir systems. So it's valid for systems that not the large variations in component and molecule weight and things like that. And Dalton's partial pressure law assumes that each component in the vapor behave as an ideal gas. In practice, the ideal gas assumption places an upper limit of pressure of 50 to 100 psi. Just if one bar or a few bars.
Can you explain this, the last sentences?
This one.
Number 2.
This, yeah, it's that the ideal, when I compress a system, there are no ideal gases anymore. They don't behave as ideal gases. It's only at ambient conditions or very low pressures that they behave as ideal gases. As soon as I compress them, the collision in between the molecules are affecting the system. So this theoretical approach that is often used in physics and try to describe theoretical fluid systems is not valid for when we are working with the petroleum systems. And then there is also more from a thermodynamic approach. We can look at Gibbs. So theoretically, ideal chemical potential for ideal gases is based on Gibbs free energy, and we have a standard state chemical potential, and we have a state function, and we can express the chemical potential based on this equation. And for real gases, they have modified that equation, and we have by adding a function of state terms fugacity into this equation. So then we have, instead of Gibbs free energy, we have just free energy, and we have the fugacity component as a part of trying to describe the thermodynamics of the system. And then for the same system here, so then we have a fugacity of the gas phase, and we have a fugacity of the liquid phase for the individual components. And then the fugacity of a mixture could then be expressed as the composition of the individual components in the gas phase multiplied by the fugacity of the individual component as a pure component. And the same for the liquid phase. And then we have that the equilibrium constant could then be expressed as the fugacity of the liquid phase divided by the fugacity of the gas phase for the individual component, pure components. Yeah, but the definition of fugacity or the approach with fugacity is that it only take into account the interaction with molecules of similar type. So the more ideal gas systems. In petroleum mixture, each component will also interact with a larger number of other molecules, so it's not valid. So methane is interacting both with ethane and is also interacting with the heavy components in the oil, like asphaltenic material. So this approach, which is typically used in thermodynamic description and chemistry to describe chemical equilibriums, is not valid for these complex petroleum mixtures either. So then there is some empirical approaches of trying to describe Ki values. So there is a set of Ki values that was developed for low shrinkage oils, and the Katz and Akmuk did it, and Roland has made some values for gas condensates, and there are also handbooks with a lot of Ki values for different type of systems. So we can so this is in a way a typical chart of this. So if you follow, this is the behavior of methane in the system, and all components. So we have different components from C1, C2, C3, C4, C5, C6, C7. We have the pressure here, and we have the equilibrium constant here. And it seems that all components have a converged pressure for the system. So if I go in at the lower pressure here, I can find my Ki value for the C1. I can find it for C2, C3, C4. So then I have at least it's not the absolute. So the main problem is in a way to select or find a chart that have or a short series with correct converge pressure, because all fluids have different compositions. So they are made for a specific fluid with a specific composition, and so it don't fit exactly and it cannot be used for absolutely any type of reservoir fluids. So that's a problem with using it, but it exists and it's a possibility if we need it and we don't have a PVT simulator to do the calculations for us. And that's what we are coming back to. So what we are doing and also what's been done in a PVT simulator is based on trying to simplify the equations that we need to solve to have a proper approach to describe the behavior of the fluid. So flash calculations can be done simplified. We can do it at bubble point, because at bubble point we only have one phase. And at the dew point we only have one phase. So then it's easy, and then it's easy to make the phase envelope, so I can, at different temperature, I can go in and I can describe the bubble point at the individual pressure and temperatures, and I get the bubble point line. And in the same way, I can get the dew point line, and that's what we are doing in the simulator. It changes temperature and pressures, and we get the dew point line for the system. And if I have a converge between the bubble point line and the critical point, is a good, is not the evidence, but is a good indication that the PVT simulator is able to handle that type of fluid. And definitely we can also use it in separated calculations by this flash calculation approach. So flash, you take if it's suppose that the system is in the two-phase region at P and T, we can do a flash calculation based on if you have 1 mole of initial fluid. And then that will be separated at the specific pressure and temperature into a gas phase and a liquid phase. And I need to know the composition of these fluids. And then I will have a mole fraction of gas, and I will have a mole fraction of liquid. So the mole fraction of liquid plus mole fraction of gas is equal to the feed, which is 1 mole. So then I have a composition of the individual component in the gas, and I have a mole fraction of the total gas component. So then I can put up the 4 equations. I have L liquid plus vapor should be equal to 1 mole fraction of that. I have a SAT, that is the vapor, mole fraction of vapor multiplied by X, the individual X components, plus the liquid fraction of multiplied by the composition of the individual components, and sum it up. And then I have that the Ki is equal to the mole fraction of gas divided by mole fraction of liquid. And I have the 4th equation that the sum of X's and sum of I should be equal to the SAT, and that's equal to what? Yeah.
I think number 4, sigma xi is equal to 1.
Yeah, equal to SAT.
No, plus, not plus sigma, equal to I.
Well, everything needs to be summed up to SAT. Yeah.
No.
Maybe it means that the second equal sign has to be changed into the plus.
No.
What do you mean?
The plus should change to equal.
No.
Okay, so I understand what he's saying.
So X is for liquid and Y is for gas.
Yeah.
No.
So
What
it should be added, and that is equal to the Z.
Yeah.
That is equal to 1.
Yeah.
That is equal to
Oh.
1.
No,
Yeah.
for example, if you have 1 mole of mixture,
Yeah.
and then it goes.
Yeah, but the start for the flash calculation is I said that I have only 1 mole.
Yes.
So I always sum up everything to 1.
And then in gas phase, you have 0.17, for example.
So I can have this is typically if this is 0.1, the V is 0.1, this is 0.9, and then I have individual components of the gas. And that's what we are doing here. Okay. We move forward. So flash calculations. I can combine these equations 2, 3, and 4, and then I can express the composition of X as the set divided by L plus K multiplied by the fraction of V. And I have the component of gas components should be set multiplied by L divided by K for the individual components, but plus V. And that gives us these 2 flash equations. So 1 flash equation for the liquid phase and 1 for the gas phase. And then I can solve these equations by iteration for the individual situation I'm working on. And I can put in, so L plus V, so that an L plus V should always be equal to 1. And typically what we are doing then is in the reservoir simulator, they're doing a Newton-Raphson iteration to get. So I have a system here. So I put up my flash equation here for the liquid phase, expressed as L. So that's for the gas, but I express it as L. And I said that it should be equal to 1. So I tried to find a solution for the flash equations. And that's, if I have a curve like this describes my system. And then I can take, instead of expressing it as V, I can say that V is equal to L minus 1. And then I can express this equation. One unknown. And by Newton-Raphson interaction, if I put in a value for, suppose a value of L, then I get a new values that are closer to my solution. If I take the tangent to L0 for the function, and I get the new L1. So L1 is L0 minus my function with the L equal to LO divided by the derivative of the function.
And number 1, if L is equal to ZI, left. Yeah.
Yeah.
There is a sigma, yes?
Yeah.
And it was.
So this is the way the simulator is doing it, and we can easily do it on by hand too, if we need to do these iterations. So this is, I just put up an example I found on explaining this iteration. So I have I choose a value of XO that is seems to be reasonable. And then I can add that into this equation here, the function divided by the derivative of the function. And then I come closer and closer to the correct value. I don't need, typically you just need 2, 3, 4 iterations, and then it's close to the correct value. So here, after how many? 1, 2, 3 iterations. I have a value very close to the real root for that in this example. So it's a simple way to do and rapid way to do the calculation. So it's easily solved. And this is in a way the way we do if you need to do a calculation of the bubble point. I'm going down in pressure. So at the flash equation, give the composition at the first bubble of gas formed. So I can use, for calculating bubble point, I can use the flash equation for gas and say that, okay, when the first amount of gas is formed. And then we said that at the bubble point, L should be equal to 1, liquid phase, only liquid or only except 1 droplet of gas, but close to 1 then. And I have a amount of vapor that is close to 0. And then I have a simplified equation describing the composition of I at its point. So PB is determined by determining Ki values at different supposed values of PB. And as a rule of thumb, if I take the SAT multiplied by Ki and is larger than 1, okay, page up. Okay, there we are. Then I'm in the two-phase region. If I have a set I multiplied by Ki, then I am in. So you just to be able to describe it, and then okay, if that don't fit, do a new calculation and come up closer to the value. And in the same way, that's the way we approach to calculate the dew point. Now I take in the liquid equation, set that xi is equal to that, and at the dew point I know that the vapor phase is equal to 1, and liquid should be equal to close to 0. It's when the first liquid droplet is formed. And then I can simplify the flash equation. So at the dew point, I only have the SAT divided by the equilibrium constant. And also here, if the SAT divided by the equilibrium constant is larger than 1, then I'm in the two-phase region. If it's lower, I should be in the gas phase region. So gas phase and two-phase region for the dew point. And that's the way we're calculating bubble point lines and dew points line in PET simulators, based on that. So my plan now is a little bit more on separator calculation. So instead of taking a break, I'll probably continue a little bit above, and then we finish after that. So, and separator calculations is in a way based on the same flash calculations, but we do it in flashing in several steps. Also here, I have a composition of fluid coming from the reservoir, go through different separator stages where I have equilibrated systems, and I have a gas fraction and a liquid fraction. And the liquid fraction is going further into the next separator stage. And the gas has left the system. So then, based on the separator calculations, I can, in a way, do the calculations I need, for example, to be able to predict the PO factor or the PG factor for the system. So it's important parameters when we are going to calculate the in-place reserves and things like that. So separator calculations. Also here, I say that I have 1 mole of fluid that is going into my system, and then I separate it into at the pressure separator stage 1, L1 and a V1, and then the liquid phase is moving further into the next separator, and I get the L2 and a V2, and that's the procedure further. And then I end up at the end with the last separator. And I can back calculate, hopefully, the information I get through the separator system, back calculate it to the reservoir conditions. That's my hope. So if we take a look and say that at the separator stage J, okay, LJ and VJ are mole fraction of liquid and gas at each separator stage. Then I can express the amount of moles of stock, of mole fraction of stock tank oil that is produced here. So the mole fraction here should be equal to the N at the last separator stage by multiplying 1, Z is equal to 1, and multiply up L1, L2, L3. That gives me the total number of moles that are in the liquid phase at stock tank conditions. So P from J equal to 1 to K multiplied by LJ. That's the number of stock tank oil moles. And the gas, number of moles of gas at stock tank condition is then 1 minus the number of moles or mole fraction of stock tank oil. And I have simplified equation for doing it. And the volume of gas at standard conditions is then the number of moles of gas, mole fraction of gas at standard conditions multiplied by Vm, the molar volume of gas. Simplified equations to do by separator calculations. I have an expression how to calculate V and L, L1, L2, L3, and V2, V3. But that's, as I said, to do separator calculation based on that, we need to have the composition analysis. We need to know the composition of the set. But today, this is handled in the separators. Or we can do it in the lab. And that's what typically been done in the lab, where we're doing in a PVT report, there is a separator you're doing a separator calculation or experiment. Okay, so that's the way. So we can simplify the equation and get a reasonable explanation to how to calculate individual components here. What's needed further for further calculations. So I know that the volume of stock tank oil is the mass of stock tank oil divided by the density of stock tank oil, and that the mass could be expressed by the number of mole fraction of stock tank oil multiplied by molecule weight of the stock tank oil. That's measurable, and the density of the stock tank oil is also measurable. And I have the total GOR, that's equal to the volume of gas at standard conditions divided by volume of stock tank oil at standard conditions. And I can also do a calculation of the GOR at the individual separator stages. So then it's the volume of gas divided by volume of the GOR is volume of gas at each individual separator stage divided by the volume of stock tank oil. And that can be expressed in when we take account the number of moles at the individual compositions here. And then I can put up an expression for the GOR at the individual stages, and that's by expressing the volume of gas. That's L1 multiplied by L2 to L minus 1 multiplied by V. To L J minus 1, and don't multiply by the volume, the mole fraction of the gas at separator stage 1, multiplied by VM. And then the number of moles of stock tank oil is the sum all the way up. So then I have Lj to the last stage multiplied by molecule weight of stock tank oil divided by density of stock tank oil. So this part here is following against this part. So it's a simplified equation set to calculate the GOR at the individual stages. And this is in a way, so this type of separator calculations is important when you're going to decide the optimum pressure at the individual separator stages. So that's what we are doing. So we test it out with different pressure and try to minimize the GOR at the individual pressure stage. And at the end, we try to minimize the total GOR for the system, if you have 2 or 3 or 4 separators. And we look further into how to calculate the BO and BG based on the same information. So, and the BO, the volume factors of oil and gas from separator calculations could be expressed as, if I still have 1 mole of reservoir fluid, I have volume of oil. So the BO is the volume of oil at reservoir conditions divided by volume of stock tank oil. So separator calculation is in way that through the separator we get the most correct volume of stock tank oil. And that's by maximizing or reducing the GOR in each separator stage, we maximize the volume of stock tank oil. And that could be expressed, number of moles of the volume of stock tank oils, number of moles of stock tank oils multiplied by molecule weight divided by the density. And this is expressed for the number of moles of stock tank oil totally. Sum up all the liquid fractions at each separator stage. And the volume of reservoir oil is volume of oil at reservoir is the mass of reservoir oil. No, mass of oil at the reservoir condition divided by density. So BO, typically BO values that we get is large for larger than 1 and up to 2. Higher for gas condensates. So if you are supposing a wet gas or an undersaturated gas condensate system, then the BO should be in the same way, and the volume of reservoir fluid can now be used by the equation of state. If you know the set, and the volume of Stockton coil is measured values. And the BG is then the volume of gas at reservoir condition divided by volume of gas at standard conditions. Small value, as you saw in the exercises last week. And that's could be expressed by the equation of state. And this one is the number of moles of gas multiplied by Vr. And that's equal to 1 minus number of moles of Stockton coil multiplied by Vr. So easily calculated based on the data that we gain through separator calculations. So that is in a way the approach on vapor equilibrium calculation. As I said, is important to be able to do it, and BO and BG factors are important when we are evaluating the in-place reserves, and also generally to understand what's happening for the reservoir fluid through the production process. So we will have, I think there is in some of the exercises some examples of doing separator calculations. So you are simplified the way to solve the problem. So I don't have put up any examples here for it. So that's what was the plan for today. So vapor equilibrium calculation is important enough, but most of the today, most of that is solved in PVT simulators and get more accurate values. But some people probably have to work with the small reservoir fields all around the world, don't have access to advanced equipment, and sometimes you need to do predictions of these values. And so now we have a way to approach that with limited information available. Okay, so next week the plan is that the student assistant will take the Thursday lecture for exercises, problem solving. And week 42 is the plan for the last lecture that I am planning to do. I will look into gas condensate calculations and also look a little bit into equation of state to try to describe what we are trying to do in PVT models. They are based on equation of states. And then we have a few more weeks that is linked to exercises. So we have put up a plan that will probably continue until week 45, and the exam is in week 48. So that was my plan for today. Any questions anywhere? Anyone on Zoom that have any questions? Been silent today?
No, sir.
Okay, that's good. So as I said, we are not going to do very advanced vapor equilibrium calculations on the exam, but be aware of that. That's the way we approach this important part of the calculations, and it's today mostly done in PVT simulators. Yep, that was my plan. Anyone? No, everything's okay. Anything you want to share with me regarding problem solving or the other part of the geo part? Hope it's not too many videos that are getting too bored. Not too long, so you are able to start sleeping. So I hope everything goes fine on that, and I know that there is at least have been some plans that CD will have some sessions also on Zoom. I think she has planned that. Hopefully everything's okay. So good luck.
Feedback for Siri.
Huh?
Can you give some feedback to Siri?
Yeah.
I asked if she can talk a bit slower in the videos because she talks so fast. It's
Oh yeah, okay. Not high, but slow.
Yeah.
Yeah. Okay.
a little bit slower.
Okay, good. I will tell her that. We'll see what she managed. She already have produced the videos. It will. You can put it on slow motion play. Turn down the speed of the presentation. The video speed. Okay.
Regarding the 3 labs of PVT,
Yeah.
will there be questions and exams from them?
Yeah, definitely. We will focus on that in the exam. Question around what's happening in the laboratory, but not specific to actually what's happening in the laboratory, because there are people all around the world that has not been able to be in the lab.
Can you repeat, because I'm not sure.
I said no, not specific questions that are linked especially to what you are doing in the lab.
Yes.
So the PVT simulation with, for example, in exercise 3 will not focus very much on that, but in the exam, but definitely I've been through in the lecturing on PowerPoint determination and flash determination of what you are doing in exercises 1. We also looked into what we are doing in GC analysis, composition analysis. So you should be aware of that. So. But the things linked to these 2 exercises is definitely something that will be questioned in the exam. Yeah. But in such a way that also people who have not participated on the physical laboratory activities will not be able to answer the questions. Yeah. Good. Then I end the session.